This is the second part of the first lecture. We will continue with the limits. And in this time, we talk about one-side limit. And we have two sides in the limits. And the first one is the right limit. It is the limit that, let's say we have a point A, and we approach this point from the right-hand side, and very little, arbitrarily very small numbers. As in the previous example, it was delta, I guess. With delta, arbitrarily small number, we approximate to the delta A with the delta, and then it approximates into the projection of f to the fx minus L, which is point L. It's approximating to the L. And its mathematical definition is if fx is defined on some interval, say a and b not involved in the interval, extending to right of the x equal to a. And if we can ensure that fx is as close as we want to L by taking x to the right of the a and close enough to a, then we say fx has the right limit L at x equal to a, and we write and show it like limit of fx x approaching a to from right hand side. The definition of left limit is also similar, very similar. In this time, we're approaching to the a point A, which is x equal to a, from the left hand side. If it is arbitrarily small enough, approaching point, approaching interval, and then we say that it has a limit on x approaching x at a from left hand side, and it's denoted by a minus sign above of the a, and the right hand side limit is symbolized as a plus sign above of the a. We can denote it like this. And we have the continuity. In order to check a function is continuous at an arbitrary point A, the following conditions needs to be satisfied. Continuity can be denoted like this. It's actually limit of fx at point x. X goes to a. The limit has to be equal to f of a, and it actually requires three things. One of them is at point A, the function f has to be defined, which means a is in the domain of the f, and there is no indefinite situation. And the second condition, limit of fx, f of x goes to a, it has to be exist, which means left and right hand sides limits are equal to each other. And finally, if the limit of f at point x equal to a has to be equal to f of f. The three conditions are satisfied. When these three conditions are satisfied, we say that the function, the limit of the function at a is continuous. We can continue with an example for um, discontinuity. Um, we have an function f, which is the absolute value of x minus 2 over second power of x plus x minus 6. And the question, the example, wants us to find the limit of fx at the right-hand side at 2, left-hand side at 2, and the limit of fx at exactly on the 2. And here um, we have an absolute value. If it is positive, let's say if x were 3, it would be a positive, and we can take out these x minus 2 to outside of the absolute value as positive, which is x minus 2. And therefore, when we look at the limit at 2 from right-hand side, we define it like a value that greater than 2, but arbitrarily small addition is here. It's, you can think of like 2.00001, which is greater than 2, and it's caused this absolute value to be positive. Therefore, we can take out this part as a positive from the absolute value. Therefore, we can write it like this: x minus 2 over second power of x plus x minus 6. And then you notice that the 2 value is making the denominator indefinite, and make it 0, and it the fraction is becoming an indefinite. Therefore, we need to take it apart to the denominator as x minus 2 times x plus 3. Therefore, we can cancel out x minus 2 parts on numerator and denominator. After that, we only have 1 over x plus 3 at the limit of the function now at 2 from the right-hand side becomes 1 over 5. We already found the right-hand side limit, and then we need to check the left-hand side of the limit at point 2. We already said that it's denoted like this with a minus sign. Since 2 minus is arbitrarily smaller than 2, the absolute value is become the x minus 2 becomes negative because it is smaller than 2. The x value is smaller than 2. Therefore, we can write it like minus times x minus 2 over second power of x plus x minus 6. And then, as same as in the above example, we need to write it like this. And then the x minus 2 terms are cancelled out each other. And then we ended up with minus 1 over x plus 3. And at the limit of the function at point 2 from left-hand side becomes minus 1 over 5. So as we see in the continuity checks, the second part says that let left and right hand side limits has to be equal. In this situation, we have a 1 over 5 in the right-hand side limit, and we have the minus 1 over 5 limit on the left-hand side limit. Therefore, they are not equal. Therefore, we can say that the limit does not exist. continue with discontinuity. When one of the previous properties is not satisfied, we say that the function fx is not continuous or discontinuous at point x equal to a. We already talked about the case in here. And if we illustrate it and talk about on an illustration, there are two discontinuity that I want to talk about it. One of them is jump type discontinuity, and the second one the infinite type discontinuity. As in the seen in the figure, we say that there is a discontinuity in the integer points of x-axis, like 1, 2, 3, and 4, because if you look at the integer points, if we approach to the 1 on x-axis from the left-hand side, it is actually approaching to the 1. Pardon, it's actually approaching to the 0. But when we're approaching to the 1 from the right-hand side, it's actually approaching to the 1 on the y-axis. We can check that on the other points. And let's check the point 3 on the x-axis. When we approach to the 3 from the left-hand side, it's actually approaching to the 2. It is clear. If we approaching to the 3 from the right-hand side, it's actually approaching to the 3. So we can say that the left and the right-hand side of the limits are not equal. Therefore, we can say that those are not equal to each other. And it's an discontinuity. And actually, we can give an example. It's not an example, actually, but it can be an example. In this situation, it is the version of partial function. We can see here that when we are approaching to x, which is involved in from the 1 left-hand side, in the left-hand side, when we are approaching to the 1, it actually gets the value 0. And when we're approaching to the x equal to 1 from the right-hand side, it actually gets the fx function, gets the value of 1. Therefore, this causes an discontinuity. And we have the second discontinuity type, infinity type discontinuity. In this figure, as x approaching to 0 from either side, the values of fx are positive and grow larger and larger. So the limit of f of x as x approaching to 0 does not exist, because when we're approaching to the 0 on the x-axis, it's become larger and goes to the infinity. And also, when we're approaching to x at point 0 from the left-hand side, it is also becoming larger and larger and goes to the infinity. It's causing discontinuity. Some examples of limits and special cases. We check the limit of infinity. We have an type of function that 1 over rth power of x, and x goes to minus and plus infinity. It's our first theorem for the limit. If the power of x here is greater than 0 and the function is a rational number, then we can say that the limit of such a function is goes to 0 when x goes to infinity, minus or plus, it doesn't matter. It's equal to 0. Um, we can check this in an example. We have a limit which is x goes to infinity, and we have a um, function such as 3 times and second power of x minus 2 and over 5 times x second power of x plus 4 times x plus 1. In order to evaluate the limit of the function, we need to divide both sides, the numerator and the denominator, by the highest power of x that occurs in the denominator. In our case, it is second power of x, which has the highest power in both cases. When we divide denominator and numerator by second power of x, in here we get the second power of x cancel out each other, and we ended up with 3. And then the first power of x and the second power of x cancel out, and it's simplified as minus 1 over x. And there is no x term in here, therefore you can just write it like minus 2 over the second power of x over the same things are applies to the below side. The x squares are cancel each other, and we ended up with 5 plus 4 over x and plus 1 over second power of x. From theorem 1, we know that the limit of rational functions goes to 0 when x goes to infinity, minus and plus for r greater than 0. In here, the r is equal to 2. It is also 2. In here, the power of x is equal to 1. It is equal to 1. Therefore, these terms are goes to 0 since the powers are greater than 0. Hence, we ended up with 3 over 5. Okay, we have the second example. And in here, the similar approach is applied. We want to use the theorem 1. Therefore, we check the highest power of the x, which is here, the highest power of the denominator in here, which is the x here. When we divide the both sides, denominator and numerator, by x, we get ratio x plus 1 over 3 over x minus 1. As you can see here, by using the theorem 1, in here r is the power of x is greater than 0. We can say that it goes to the term is goes to the 0, and then we ended up with x plus 1 minus 1. Since x goes to infinity, actually the limit goes to infinity, but there is a minus term in here, negative term in here. Therefore, the ratio is become minus infinity. And we have the second theorem, which is famous skews theorem. Also, it's called a sandwich theorem. But before that, we need to give an additional theorem, theorem 2. If f of x greater than and equal to g of x, then x is near a, except possibly at point A, exactly the point of at A, and the limit of f and the g both exist as x approaches to A, then we can say that under the image of limit, the functions also preserve the inequality in their values. Therefore, limit of f of x goes to a smaller and greater than, smaller and equal to limits of g of x goes to a. The condition is satisfied, holds. And then we have the theorem 3, which is using the theorem 2. As we already said, it's a skew theorem, also called sandwich theorem. If f of x smaller than and equal to g of x, and it is smaller than equal to h of x, when x is near a, except at the same time, except possibly at a, and if also limits of f of x at point a and h of x, limit of h of x at point a equal to L, both are equal to each other, then we say that the limit of g of x equal to L. Since we already know that, since we take the limit, we can take those limits in here. We already know that limit of hx goes to L, and also limit of f of x, at point A goes to L. Since there is two inequality, and g of x is smaller than hx and greater than f of x, limit of g of x has to equal to L. We can give more detail, or we can increase the understanding of the skew theorem with additional examples, 2 examples. In the first example, we need to show that limit of x squared times sinus of 1 over x at limit 0 equal to 0. In order to use it, we need to note that the sinus function has the values between the range -1 and 1, which can be demonstrated as like this, and any inequality remains true when multiplied by a positive value, such as second power of x all the time is greater than 0 or equal to 0. We have at the first term, at the beginning, it's the interval for the sinus 1 over x is greater than or equal to -1, and it's smaller than or equal to 1. And then we already said that positive value, such as second power of x, or it could be fourth power of x. When we multiply by all the sides of the inequality, we have minus second power of x, and in the middle part we have the second power of x in 1 over x, and also it is smaller than and equal to second power of x. And we also know that it doesn't matter, it's plus or minus. When we take the limit of second power of x at point 0, it's equal to 0. Therefore, the both sides of this inequality are equal to 0. Therefore, it has to be 0 from the skew theorem. In the second example, we need to show that here, when n goes to infinity, we have a -1, the nth power of -1 and over n. equal to 0, we need to show that. We already know that from the theorem 1, I guess, in the previous part, since here the r value is equal to 1, therefore this is goes to 0 when n goes to infinity, and it doesn't matter at the same time. The minus 1 over n is also goes to 0. Therefore, we can choose the function of or function from the left and right hand sides with those values. And since they are goes to 0, our function's limit at point and as n goes to infinity becomes 0. Okay. Now it is our last part of the lecture, which we are talking about the series and sequences. The sequences also contains the limit. There is also limit calculations in the series and sequences, or there are also some examples related to limits. We can give a brief explanation of series, but after that, I will continue with the sequences. A series is simply the summation of the sequences, which can be thought of as a list of numbers written in a definite order, which is we have sequences here. Actually, it's a one sequence. It's a sequence, and those are the terms of the sequences. The first term of the sequence is the A1, and the second term A2, and the third term and nth term of the sequences. And the summation of those terms gives us the series, but it's the list of these terms gives us the sequences. And the sequence can be denoted as the following: AN, or we can I don't remember the name of this bracket type, but it is AN, and it starts with A equal to 1, and it goes to infinity. And for every positive integer, and there is a corresponding number AN, their importance in calculus is representing the function as sums of infinite series. When we talk about the series, the summation is used. And when we talk about the sequences, the list of the terms are employed. For instance, finding the integral of a function by expressing it as a series and then integrating each term of the series. Actually, we talk about here is that why we are using this series, because in such a situation, for example, the power of e, second power of x minus of fx, it is very hard to take the integral of this function. It's very hard. Therefore, we need to extend this function to a series and take the integral term by term in the series. It makes the our jobs to be easier. Here are some examples of sequences. Here is the 1, 2, 3, 4, and 5, which is positive numbers. This is the sequence of positive numbers. And the general term in here, the general rule in here, that the previous term is summed with 1, and it creates the next term in the sequence. just adding 1, we create a sequence in here, and here is the first term of the sequence is equal to 1. We have the second sequence. Here is the our sequences contains the rational numbers. The first term of the sequence is minus 1 over 3, and the second one 1 over 9, and the third one minus 1 over 27. It goes like this. As you notice here, you can guess the second general term. It's actually, if you take the first term of the sequence as minus 1 over 3, the second term is positive, and it is the second power of the first term. Therefore, we're taking the terms powers, which is nth powers. This is the 1th power, this is the 2nd power, this is the 3rd power, which is minus. Therefore, it's actually nth power of minus 1 over 3. Some terms for describing a sequence. When we want to describe a sequence, we need some descriptions, such as we have this first description, bounded sequences. We can talk about the bounds of the sequence. And there is a mathematical definition here. L is lower bound for an sequence if an greater than and equal to L for every n equal to 1, 2, 3, and so on. We can say that it's a lower bound because it's not smaller. N is not smaller than L here. Therefore, it's become a lower bound in here. The sequence is bounded above by k if a n smaller than or equal to k for every positive number of n, which is n is not greater than any of the members of the sequence n is greater than k. So we can say that k is an above bound for our sequences. For this, we have an example. We have a n sequence, which is equal to nth power of minus 1 over 2 here, and it creates a sequence such as minus 1 over 2, 1 over 4, and minus 1 over 8, and so on. As you can see here, it is clear that we have some positive and negative terms in our sequences. And also it is clear that in the positive terms, the greatest value is here 1 over 4. It means that the sequence will not be any of the member of the sequence will not be greater than 1 over 4. Therefore, we can say that 1 over 4 is our upper bound in here. It's bound the sequence from the above. And also, we have the negative terms in our sequence. And in here, the smallest terms is here is the minus 1 over 2, and it's getting bigger. And since it is the smallest value in our sequences, it is the lower bound for our sequence. And the second definition, whether or not the sequence is increasing or decreasing, and also some additional terms are in here, non-increasing, and also the non-decreasing terms. The first one, if an plus 1 greater than and equal to an, which is the previous term in the sequence for every positive integer n, then it is a non-decreasing sequence. And in the reverse case, when the next term in the sequence is smaller than the previous an and equal to an, we say that it's a non-increasing sequence. Why we call it non-decreasing or non-increasing? Because there is an equality in the inequalities. Therefore, we need to say that it's a non-increasing. If we don't use the equality in here, we can say that the sequence is actually decreasing. But there is an equality in here. We need to say that it's a non-increasing sequence. The difference is that. And also, this is the actually the increasing and decreasing sequences definition for the increasing and decreasing sequences. Here is the a and n plus 1 greater than an. Therefore, for every n, we say that it's an increasing sequence, and the reverse case, we say that it's a decreasing sequence. And we have some examples in here. An, which is equal to second power of n, is an example of a non-decreasing sequence and also increasing sequence. And we have the bn 1 over n is for a non-decreasing and also decreasing sequence. When we write down all terms for natural numbers or positive integers, we get 1, 4, 9, 16, and 75. These are actually increasing sequences. And we have the second sequence in here, which is Vn, and it is equal to 1 over 2, 1 over 3, which is decreasing as it is seen in the, it is clear, convergence of the sequences. And here is a formal mathematical definition of the convergence of the sequences. We have a sequence here, an, and it is a infinite sequence, which is n goes to the infinity, and L is a number. Then we say that when n goes to infinity, the limit of an is equal to L if an gets arbitrarily close to L as n increases. It's actually very similar to the limits definition. If limit of an as n goes to infinity exists, we say that the sequence converges, or the sequence is convergent. Otherwise, it diverges, and also it is divergent. We can illustrate it in the figure. As it is seen here, it takes the values around the L, and then when it gets bigger, we see that each point of the function, not function, in the second, it's getting closer to the point L here when n goes to infinity, and we can think of the convergence of the sequence as like this, and this it is very similar to the, as I said before, it is very similar to the limit logic. As the an values gets bigger and larger, and goes to infinity, the sequence takes the values around the point of L, and the neighborhood in a positive value of epsilon is state um, state the L in the interval. Therefore, our sequence is convergence, and the limit is convergence to the L. And here are some simple examples. 1 over n is a simple example for the convergence sequence. Since limits of 1 over n goes to the infinity is equal to 0, it is very clear that if we can make the sequence arbitrarily close to 0 by choosing n large enough for the values of n, which is 10, 110,000, and 10,000, or general term equals to 1 over 5, 1 over 1, 1 point, 1 over, not 1 over, it's 0 0.1, 0 0.001, and 0 0.001. As you can see here, it is clear that when the n gets larger, or projection and the term of the sequences are getting smaller and becoming more close and closer to the 0. And we say that the sequence converges to the 0. And we have the second example, which is an example for divergent sequence. And our general term for the sequence is 2 times n. Here, when n goes to infinity and gets larger and larger values, our sequences getting larger. Therefore, we cannot say that it is the limit of the function is not equal to a real number L. Because it goes to infinity. Therefore, you can say that it's divergent sequence. And we call it the sequence is diverges to infinity. We need to talk about some limit laws for sequences. We have two sequences and they are convergent, and we have a constant here. Then our first law is limit of, there has to be bracket here, limit of an plus bn. When n goes to infinity, the summation can be written under limits as two parts. Limit of an plus limit of bn, n goes to infinity. This is our first law. And the second law, when we multiply and sequence, general term of a sequence by a constant, the limit can be written as it is, as like this. We can take out the constant outside of the limit, and it's become c times limit of an and goes to infinity. And we have the third law, a limit of a constant gives itself. And we have the law for multiplication. The limit of two sequences that are multiplied by each other can be written as partially. The limit of an times limit of bn, and goes to infinity. And we have the fifth law, which is for the fractions, rational sequences. The limit can be written as like this. We can divide the two sequences as in the scene, but there is a condition. limit of Bn does not equal to 0 there because it's cause an indefinition. And here we have the power of n sequence, and we can take out the outside of the limit the power if p is greater than 0 and an greater than 0. There is a special case condition here. And some examples for the sequences. In our first example, we need to find the an, limit of an goes to 0, and our general term for the an is n over n plus 1. As said before, the solution is similar to the limit part. We need to divide the numerator and denominator by the highest power of n that is in the denominator. After that, we will use the limit laws. And here is the highest power of n is 1. Therefore, we need to divide both sides with n. When we divide both sides by n, we get in the upper sides 1, and in the lower sides 1 plus 1 over n. As we already know that 1 over n, as n goes to infinity, it goes to 0. Therefore, pardon, it's the actually we are using here the fifth law in here. We can partially write the limits, and then when we take the limits, it goes to 0. This is a constant function. It is the third law, and they are equal to itself. And we have the ratio 1 over 1, and it is equal to 1. And we can say that the sequence is the convergence. It's converged to the 1. And we have the second example here. We need to find the ratio n over the second root of 10 plus n when n goes to infinity. The similar strategy has to be used in this part. In here, the highest power is actually n, not root of n, because actually the power of this n is 1 over 2, which is smaller than 1. Therefore, we need to divide the both sides by n here, and also for the simplicity, we can say that we can also write the n as the second power of n and taking the second root of the n. The root and the power is cancel out each other, and we ended up with power of 1, first power of n. Therefore, we don't change anything in here. We can divide both sides with this term. Then we divide it. We know that this is equal to n. Therefore, these cancel out each other and becomes 1. And then we divide the below side with the square root of n, second power of n. We get 1 over 10 over second power 1 plus 1 over n here. And then we take the limit here. We already know that the terms are goes to 0. Therefore, the below side becomes 0, and it's equal to any number, any constant number, any number that when divided by 0 goes to infinity. There is a difference when the number is negative and divided by 0, it goes to negative infinity. And hence, we can say that the sequence is divergent here. And we have the third example. We check the limit of the ln of n over n here, whether or not it's convergent or divergent. We will use here a special rule, which is called L'Hopital, L'Hopital's rule. Here it's clear that as n goes to infinity, the denominator and numerator go to infinity here, because natural logarithm can go to infinity as n goes to infinity, and also n is goes to infinity here, and then we have the ratio of infinity over infinity. This is undefinite situation. For such a situation, we can use the L'Hopital's rule here by assuming that it's a function of n here. L'Hopital rule is simple. We just need to take the derivatives of the numerator and denominator here partially, and we will talk about the derivatives on the next lectures. But in this situation, the derivatives of natural logarithm is 1 over n, and the derivatives of n is here to 1. In this situation, taking the limit when n goes to infinity is very easy, since we know that when n goes to infinity, 1 over n goes to 0, and we already have in the below side 1. When we divide 0 by 1, we get a 0, and then we can say that the sequence is convergent, and it is convergence to the 0. We have the fourth rule, fourth example. Determine whether the sequence an equal to the nth power of -1 is convergent or divergent. When the term of the sequence are written out, we see that it's repeating itself. It's actually starting with -1 and then +1 and then again -1 and then again +1. It goes like this. Therefore, if we illustrate it in the figure and examine in the figure, we see that for the first term of the sequence, it gets the value of -1. For the second, it gets the value of 1, and then it's turned back to the -1. It's turned back to the 1. It actually moves when when n gets larger. It moves uh, uh, like oscillating. It gets down and up and again down and then up and then go. It's like this. It goes like this. It actually fluctuates, and it also can be said that it oscillates between the values minus and 1. Therefore, we can say that this sequence does not approach any number. It is getting values of 2, -1, and 1, but it is not approaching any number. Therefore, the limit does not exist, and the sequence is divergent here. And we have the fifth example. We need to check the convergency or divergency of the function as n goes to infinity. But before that, we need to give an additional theorem, theorem 4. The theorem says that the absolute value of if absolute value of the function an, sequence of the absolute value of the sequence an, when n goes to infinity is equal to 0, then we say that the version of an without absolute value also goes to 0. If the sequence in absolute value goes to 0, the version of an without absolute value is also goes to 0. If we use the theorem, we can take the absolute value of the function here, and the sequence is become as you can see here. And we know that when we take the absolute value of a negative number and positive number, it's actually becomes positive number, and we get rid of the negative side of the sequences, and then it becomes 1 over n. And before that already talk about that, 1 over n, the limit of 1 over n when n goes to infinity, and since the power of n is greater than 0, its limits goes to 0. Therefore, by using the theorem, we can say that the sequence itself also goes to 0, and it is also convergent. And also we need to mention that theorem 4 cannot be applied to previous example, which is it minus the nth power of -1. We will talk about in the below, and also its action follows a fluctuation moment. Convergence of nth power of r in such a sequences, we say that the sequence nth power of r is convergent if r is between -1 and 1, and also my positive 1 in the interval, and the sequence is divergent for all of the values of r. As can be observed in the following figures, the left and the right hand side. As you can see here, when r is greater than 1, it's exponentially increasing, and it is not converging any real number. When r is equal to positive 1, it is constant, and we can say that it's also convergent. And when it is between 0 and 1, the value of r between 0 and 1, and 1 and 0 not included in the interval, it's approximating to 0. It's approximating to 0 here. And when the r takes the values between -1 and 0, we see that those values are oscillating, not oscillating, it's approximating to 0. The values of an becomes closer and closer to the 0 when it is smaller than -1. It is oscillating like, it has a oscillating like view, but actually it's exponentially increasing for the even values of the n in the positive side, and the odd values of the n, it's exponentially decreasing in the negative side of the an. Therefore, those are when r is smaller than -1, it's also not convergent. its divergence. Okay, we can also summarize it in the partial function in here. When r is between the -1 and the 1, it gets the value of 1, and when it is equal to 1, the, 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 the sequence gets the value 1, and all the values of r, it is divergent. Okay, we have the last two examples here. Example 1, we need to check the function 1 over nth power of 3 is divergent or convergent. We can write the ration number 1 over nth power. It has to be n. It is mistakenly written as 2. Ration number 1 over nth power of 3. We can write it as the common power of 1 over 3, and here the r becomes 1 over 3, and we already know that when the r is between -1 and 1 and 1, -1 and 1, it satisfies the following above condition, and its limits approximating to 0, and its limits actually convergence to 0. And we have the second example in here. This is the reverse example for divergence. Here's again, we have a 3 over 2, nth power of 3 over 2. In here, the r 3 over 2. Therefore, this is not satisfies the above condition. And we can say that when the limit goes to infinity, the sequence is divergent. It diverges. Okay, we can finish the lecture here and stop the sharing.